Now that we know the effect of a magnetic field on a charge or on a current, the question might arise, what's the effect of a current on a magnetic field? We start with this. Imagine a long wire that's carrying a current, for example, upwards. Now, due to that current, we are going to have a magnetic field all around the wire. Okay, these snapshots here show us the direction of this magnetic field. We have a small compass here to show us what it is. It's actually, it's going to point in a direction like indicated by this small compass. You see the red arrow and the green arrow. So your magnetic field is going to point from green to arrow, or in this direction. Now you notice it's going around the wire, which means in this point here the magnetic field is going to point this way. In this point here it's going to point this way. Always tangent to the circle, but in a direction like shown by the compass. If my current is going in the opposite direction, the direction of the magnetic field is going to be in the opposite direction. Let's look at the simulation. Okay, here is the simulation, and you notice here I can put the compass anywhere, and you notice the way the arrow is pointing. It is always tangent to the circle, but always pointing in the same direction. In this particular case, it is in the counterclockwise direction. Now if we reverse the current, you notice that this one has flipped, and no matter where I'm going to put my compass, is going to detect a magnetic field that's in the clockwise direction relative to that wire. Now this is another simulation. I'll go back to it in a second, illustrating the same concept. Oops, didn't mean that. Okay. Now the magnitude of that magnetic field due to a long straight wire is given by this expression. B is equal to mu0 I over 2 pi r. Remember, mu0 is 4 pi 10 to the minus 7 Tesla meter over amperes, and r is the distance from the wire. The further we go away from the wire, the smaller is going to be that magnetic field. For the direction, we use a new right-hand rule. Okay, in this case, the way to do the right-hand rule, we position our finger in the direction of V, which is the same as the direction of I, because remember, V, we are talking about positive charges, and I is the direction of flow of positive charges. Now, if this is our wire, what we do, we wrap our hands, we wrap our hand around the wire, our right hand around the wire. Now, I is in the direction of the thumb, and then B in the direction that our fingers are wrapped around the wire. Our nail indicates where our nails are, indicates where the tip of the magnetic field vector is. And the magnetic field, as I mentioned earlier, is going to be pointing in different directions around the wire, such that it's going to be counterclockwise or clockwise depending on the configuration. Okay, let's go back to the simulation. Okay, here we have another simulation. So we have a wire, we have a battery, a large battery, some clamps. This is kind of given us a historical perspective when people first discovered this, and so the look, it's a historical look. Now we turn on the circuit, so we make the connection. You notice there is no connection, so we make the connection. Pay attention to the direction of the compass, and voila. Okay, now to determine if that's correct, if that's all right, we are going to use our right-hand rule. So in this case, the positive lead is in this end, so the current is going in this direction from right to left. So our thumb should be from right to left, and then we wrap our hand around the wire, and you see in the bottom of the wire the magnetic field should be pointing in the same direction as the compass needle. If we had the compass needle on top of the wire, it will point in the opposite direction. I cannot do that with the simulation, but you get the idea. Now if I flip the battery, the current is going in the opposite direction, so the magnetic field is going to point in the opposite direction. Again, you think of the direction of flow, you wrap your hand around the wire, and the magnetic field is going to point in opposite directions, in different directions relative to the wire. It's going to be clockwise or counterclockwise, depending on the flow, the direction of flow of the current.